In the late 1970s, Kansas City aimed to compete as a modern convention and travel destination, and a new downtown hotel became part of that push. The project was planned under the Hyatt Regency name, and it promised more than beds and banquet rooms. It was meant to make an impression. Early on, the design centered on a tall interior atrium, a public space meant to pull people in and keep them moving through the building. To turn that atrium into a signature, the plans included suspended walkways crossing open space at multiple levels. They were not just corridors. They were a feature people would notice, use, and remember. The concept sounded straightforward. Hang the bridges from above using steel rods and connections and keep the floor below clear. On paper, the idea balanced elegance with efficiency, and it fit the era's confidence in big interior structures. As architects and engineers pushed the design forward, those walkways became locked into the project's identity. That decision carried weight because a suspended system depended on small parts doing critical work every day. Each connection, each rod, each beam had to transfer loads safely, not once, but constantly, under crowds, events, and routine traffic. The walkway concept moved from a bold drawing to a real structural promise, and the next steps would test how carefully that promise was handled. As the project moved from drawings into real construction planning, the suspended walkways stopped being an idea and became a set of exact instructions. The support concept at that point stayed straightforward. Long steel hanger rods ran from above, passed through the upper walkway, and continued down to hold the lower one too. One continuous line carried both levels. On paper, it looked clean. It also looked familiar. That single continuous rod detail got locked in as the reference everyone worked from. The engineer's design intent traveled outward into the world of fabrication and installation, where every measurement and connection had to be built, shipped, and lifted into place. Each handoff mattered. Drawings, calculations, and notes moved between offices and shops, then back again. The expectation stayed simple. Build it the way it was designed, and it would behave the way it was calculated. By this stage, the walkway support was treated as settled, not as a question still open for debate. The contractor planned erection around those continuous rods. The fabricator prepared to turn the detail into steel parts that fit and tightened correctly in the field. And the engineer's original concept remained the baseline against which everything else got checked. That baseline carried weight. Once it became the shared starting point, any later change would have to fight against momentum. As the project moved from drawings to real steel, planning shifted into the practical world of fabrication and erection. Now the question was not just what the walkways looked like, but how crews would actually hang them in place. The original idea used long, continuous hanger rods that ran through the upper walkway and kept going down to the lower one. On paper, it was clean. In a shop, it looked slow and awkward. The steel fabricator brought in a late proposal meant to make that installation easier. Instead of one rod doing two jobs, the rod got split into two parts. One set of rods would hang the upper walkway from the roof structure. Then a second set would hang the lower walkway from the upper walkway. It sounded like a small tweak. It sounded like common sense. It also changed what each connection had to carry. This was the moment where a signature feature met a real-world shortcut. The split rod detail promised faster assembly, simpler handling, and less wrestling with long-threaded steel. For the people building it, that mattered. But the proposal also created a new chain of dependencies. The upper walkway no longer just supported itself. It became the support point for the walkway below. and that quiet shift set up the next decision. The revised hangar detail moved fast. It travelled as a practical fix, not as a structural red flag. Notes and drawings changed hands, and the new connection was treated like a small adjustment to make fabrication and erection easier. Approval came in the same everyday way other shop details got approved. But this was not a cosmetic change. It quietly rewired how the walkways carried weight. With the original continuous rod, the upper walkway's support still carried the lower walkway, but the load path stayed straightforward. The split rod version did something else. The upper connection now had to hold up the upper walkway, and it also had to take the force that used to pass through as one continuous line. In simple terms, one critical piece now carried about twice what it had before. That fact never got fully chased down. No one stopped the process to run a fresh, coordinated set of calculations. No one gathered every party and asked, in plain language, what the change did to the forces at that joint. The approval effectively meant the engineer stamped the detail as acceptable, even though the real engineering check behind it did not match the new reality. From that moment, the project carried a hidden decision. It also carried a doubled demand on a single connection. With the revised connection treated as routine, the project kept moving. Steel was ordered, shop work continued, and crews prepared the atrium walkways for installation. On paper, nothing looked dramatic. The design still appeared to match the drawings that had been approved, but the meaning of that approval changed everything. A small detail now carried forces it was never meant to handle, and no one stopped the schedule to prove it. As the walkways went in, the new hanger rod arrangement became physical reality. Each connection point now had to transfer load in a different way, concentrating stress where the original concept had spread it out. The parts fit. The installation looked clean. Inspections focused on whether members were in place and bolted correctly, not on whether the revised detail had quietly shifted the math. The weakness stayed invisible because the building stood. Then the hotel moved closer to opening, and the atrium became what it was always intended to be, a public gathering space. People used the walkways because they were meant to be used. That constant, everyday traffic turned the changed connection into a high-stakes point of failure, repeated again and again under normal activity. The danger did not announce itself with cracks or warning alarms. It sat inside the structure, sealed in by progress. On July 17, 1981, the Hyatt Regency's atrium stopped being just a design on paper and became a living test. The hotel hosted a tea dance, and people arrived expecting an easy night out, music, drinks, a crowd. As the evening filled in, the open space did what it was meant to do. It drew people inward. More guests flowed onto the elevated walkways, using them as the perfect place to watch. The second floor and fourth floor walkways started carrying something no drawing could truly capture, the weight of a packed, moving crowd. People leaned along the edges, gathered in clusters, shifted to make room, then shifted again. Below them, the atrium floor filled too, adding to the sense of a single, concentrated event. This was real-world loading, uneven, changing and heavy, building minute by minute as the dance continued. Nothing dramatic announced itself in the moment. The walkways still looked like walkways, and the hotel still ran like a hotel. But the conditions had changed in a way that mattered. The space was no longer lightly used. It was crowded to its practical limits. The load on those suspended connections rose as more bodies gathered above and below, turning an ordinary social event into a high-stakes stress test. Under the weight of the crowd, the revised hanger rod connection reached its limit. It did not bend slowly and warn people. It gave way. One connection point failed, and the load shifted instantly to the remaining parts, pushing them past what they could carry. In a moment, the fourth-floor walkway dropped. Then the second-floor walkway, hanging beneath it, lost support as well. The failure cascaded. Seconds decided everything. The two walkways fell into the atrium, one striking the other and then the people below. The impact trapped dozens in a tight, crushing space where movement became impossible. Some victims were pinned under steel and concrete. Others were thrown aside and injured by the collapse itself and by falling debris. The music and celebration ended as a single violent event. What had been an elevated viewing space became the center of the disaster. Inside the hotel, the first response came from whoever was still standing. Guests and staff pulled at pieces they could lift and tried to reach voices coming from underneath. Then emergency crews arrived to a scene that did not behave like a normal building accident. The wreckage blocked access, the loads were unstable, and every shift risked another collapse. Rescuers worked in bursts, lifting, cutting and bracing, while the number of dead and injured climbed fast. In the hours after the collapse, the focus shifted from rescue to one urgent question: what failed first? Investigators treated the wreckage like a mechanical puzzle. They traced the hanger rods, the nuts, and the connection points that should have shared the weight. Step by step, they rebuilt the load path on paper. One detail kept returning to the center of every diagram: the revised hanger rod connection. The original concept spread the forces through a continuous rod. The change split that rod into two separate pieces, stacked one walkway's support onto the other. That small-looking revision mattered. It shifted the load, so a critical component carried roughly twice what it previously did, right where the connection was most vulnerable. Under the crowd's weight, the hardware did not just bend, it let go. Then everything above followed. Once the failure point was clear, the next question became how that detail reached the building at all. The investigation uncovered a broken chain of review. The change moved through calls, notes, and shop drawings, but it never received the kind of full recalculation that matched its risk. Responsibility blurred as information passed from one party to another. In the end, the disaster looked less like a mystery and more like a process that failed. In the months that followed, the collapse stopped being only a disaster scene and became a legal battlefield. Families filed wrongful death and injury lawsuits. The hotel's owners and operators faced claims about crowd safety and oversight. Contractors, steel fabricators, and engineers faced claims about design responsibility and approval. Insurance companies demanded answers in writing, not in memories. Each case pressed the same question: who had owned the change and who had checked it? Licensing boards then moved in, because this was not just about money. They examined seals, calculations, and the way shop drawings had been handled. A shop drawing looked routine, but it carried a dangerous promise that someone competent had reviewed the detail and its impact. Investigators showed that a small connection change had shifted forces dramatically. Regulators treated that gap as professional misconduct, and disciplinary actions followed. Engineering organizations also issued ethics rulings, and those rulings changed practice. The message stayed simple and hard. An engineer could not approve a design change without verifying the numbers, and could not rely on informal calls or assumptions. Firms tightened internal review, required clear written approvals, and demanded recalculations for any detail that altered load paths. Building codes and contract procedures also hardened around submittals. Accountability became a process, not a feeling. In the years that followed, the Hyatt Regency collapse stopped being only a Kansas City disaster and became a global lesson. It entered classrooms, licensing exams, and company training as a defining engineering ethics case. Not because it involved a rare material or an exotic design, but because it involved ordinary steps that went wrong. A change looked small, an approval looked routine, and the consequences proved permanent. It also marked a shift in attitude. In the late 1970s, an atrium with suspended walkways carried a kind of confidence, bold, modern, and assumed to be safe because professionals touched it at each stage. After the collapse, that confidence no longer counted as protection. The case taught that a signature feature demanded the opposite of casual handling. It demanded proof, on paper, every time something changed. So the lesson hardened into process. Modern practice treated design changes as high-risk events, even when they seemed simple and even when they arrived late. Calculations had to match the new detail, not the old one. Responsibilities had to be explicit, not implied, and independent review became a safeguard, not an insult. The Hyatt case stayed alive because it showed how failure often came from permission, not from ignorance.